If you ask a particle physicist like me what they're thinking about, the answer will likely be very big or very small, or maybe about lunch. But most of the time, we like to think of very big questions, like why the universe is the way it is, and does it have to be that way? This leads us to think about the tiny subatomic world. The reason we do that is simple. If you want to understand the universe, one thing you have to do is to figure out what it's made of and the rules that hold it together. Once that's done, you can answer questions like why planets exist instead of, for instance, a diffuse gas that permeates the cosmos. There are criticisms to this sort of reductionist approach, like those who claim that it is hard to predict phenomena like turbulence in animal biology, knowing just the laws of particle physics. And there's some merit to that statement. Still, all phenomena must not only conform to the rules of the microrealm, these phenomena originate in those subatomic rules. So it's at least important to have an understanding of the most fundamental building blocks. Our current understanding of these tiny bits of matter is that there exist two classes of particles called quarks and leptons. Quarks are found in the nucleus of atoms, while the most familiar lepton is the electron. In addition, there are four forces which are mediated by force-carrying particles jumping between the quarks and the leptons. The name we have for this model is called the Standard Model of Particle Physics. And if you want to know more about it, I made a video that gives a bunch more details. The problem is that if we want to get at the ultimate building blocks of the universe, what we currently know doesn't seem to completely fit the bill. We have 6 types of quarks, 3 charged leptons, 3 neutral ones, and 4 force-carrying particles. Plus, when you include the mysterious world of dark matter and a so far undiscovered particle called a graviton, the situation is a ridiculous mess. Some have charge, some don't. Some particles feel some forces, but not others. It's hard to imagine that the ultimate building blocks and most fundamental rules are found in this complexity. It seems there must be something simpler underlying all of this. As we dive into the world of the super-small, we encounter molecules, then atoms, then protons, neutrons, and electrons. Digging deeper, we find quarks and leptons. So could there be another layer, or 2, or 3? Well, sure. Even though they haven't been found and, to be honest, may not even exist, we already have a name for the layer below quarks and leptons. These smaller particles are called preons. But there's no reason there couldn't be pre-preons and pre-pre-preons and so forth. In short, there could be a long line of undiscovered particles before we find the ultimate and smallest particle of all. This seemingly endless ladder of particles isn't the only idea out there. One very interesting idea is that when we get to the smallest size of all, we don't find a particle, but rather an ultra-tiny vibrating string. So how does that work? How can a string explain the variety of subatomic particles we know about? Essentially, scientists assign the various different vibrational patterns of the string to be the various known particles. You can get a sense of this by seeing what happens with a single string. If you vibrate a string slowly, you get a single big vibration. If the vibration is increased, you get 2 big vibrations. Increase the vibration more and you get 3 vibrations, and so on. In the superstring model, each vibration pattern represents a specific subatomic particle. This is really cool because it means that all particle types originate from a single kind of string. The complexity of vibrations is even more obvious in 2 dimensions. Take some salt, put it on a metal plate, and drive it with a speaker, and remarkable patterns arise. In this example, the white lines are where the salt is stationary and the plates aren't moving. Where you see the metal of the plate, it's vibrating like mad, so no salt can sit there. While 2-dimensional vibrations are already pretty complex, scientists think that superstrings vibrate in way more dimensions, as in like 7 dimensions. Yes, imagining more dimensions is hard to get your head around, but it's what the theory needs to work. The dimensions we're talking about here are much smaller than the ones you're familiar with. You can get your head around smaller dimensions using this hula hoop. The hula hoop can move in the familiar X, Y, and Z dimensions of left and right, up and down, and forward and backward. But you'll notice that the hoop has a little paper sleeve wrapped around it. If you want to explain the location of the piece of paper, one way to do that is to locate the hoop center in X, Y, and Z, and then state the position of the paper on the hoop: bottom, side, top, and so on. Now, imagine that the hula hoop is small, so small that you can't see it. The location of the hoop still needs 3 dimensions to describe it, but there is still the question of where the paper is. To answer that question, you need 4 dimensions. Now, I know that some of you will say that as I move the paper around the loop, it is also moving in the ordinary 3 dimensions. And you're right. Just remember, I'm using an analogy to describe a very complex mathematical idea. The analogy is imperfect, but I hope it conveys the right idea. So, in superstrings, you need 3 spatial dimensions of x, y, and z, plus the dimension of time. That makes 4. But you also need 7 small extra dimensions, making a total of 11. Pretty mind-blowing to be sure, but if you just remember a small string vibrating in 7 dimensions, you get a decent idea of what the theory predicts. If you want to understand at a deeper level, I have 4 words for you. Go to grad school. A very important question should be on your mind. Are superstrings real? Should I believe in them? The answer is clear and unequivocal. Superstrings might be real, but you absolutely should not believe in them. They are currently a very cool mathematical idea, and there is exactly 0 experimental evidence to support them. The reason is simple. The extra dimensions of superstring theory are incredibly small, much smaller than we can access using our particle accelerators. Physicists imagine that the size of strings might be the Planck length, which is about 10 to the minus 35 meters. That's far smaller compared to a proton than a proton is compared to you. There is no accelerator built or even imagined that can explore such tiny sizes. So why do scientists study this idea that is so hard to prove? Well, first, the idea is just plain cool. But second, it's a nice and simplifying explanation that finally gives us a simple and fundamental building block that can then explain the complex world we actually live in. When people ask me if I believe in superstrings, I have to say no. But I'd like to. The idea is intriguing and compelling, and I want theoretical physicists to keep thinking about the idea. Maybe they will eventually come up with a way to experimentally verify the model. And then we'll know if superstrings are really a brilliant explanation or just another idea that didn't work.